Okay, hello everyone. Let us continue the second part of today's class. Okay. Okay, so the numerator of this equation is equal to 0.5p times 100 squared. Okay, which is equal to 0.5 times 10,000 and is equal to 5,000. And this term, okay, 0.5p times 200 squared. Okay, this term is equal to 40,000 times 0.5 is equal to 20,000. Okay, so 5,000 plus 20,000 p is equal to 25,000 p. Okay, so we can cancel the p in the numerator and the denominator, and 25,000 divided by 2 is equal to 12,500 nanoseconds squared. Okay, please note that do not forget the square here. Okay, then equation 4.22. Okay, let us go to this equation. Okay, equation 4.22. Sigma tau is equal to the square root of tau square bar minus tau bar square. Okay, so sigma tau is equal to the square root of tau square bar, okay, which is equal to 12,500, and minus, okay, this is the tau bar square. Okay, so it is equal to 75 square. Okay, 75 square. Okay, and we can use a calculator to calculate the value of this equation. Okay, so it is equal to 12500 minus 75 square. Okay, which is equal to this number, and take the square root. Okay, we have it is approximately 82.9. Okay, so it is approximately 82.9 nanosecond. Excuse me. In addition to illustrating the steps used in computing the delay spread, this example also highlights the fact that only the relative amplitude of the power delay profile is needed. Absolute power levels are not. Okay, this is evident from the fact that we arbitrarily replaced the true power level of the maximum component with a variable p. Okay, we can see that, okay, denote negative 100 dBm by p, okay, which is the largest power. Okay, this of course means that delay spread values can be measured without needing to compute the absolute received power levels, eliminating the need for complex calibrations during the measurements. Okay, what are calibrations? Let us see handout. Okay, where is the handout? Okay, here. Okay, so on page 107, problem 1, what is calibration? Solution. Calibration is the noun of calibrate, which means to check a measuring instrument to see if it is accurate. Okay. Okay, next let us see a typical root mean square, that is RMS delay spread values. The delay spread values of multi-path channels depend on the nature of the scattering, but are relatively insensitive to radio frequency over the range of frequencies typically used by commercial wireless devices, which range from about 1 to 5 GHz. Okay, a summary of measured RMS delay spread values is given in Table 4.2. Okay, let us see this figure. Okay, Table 4.2 shows the measured RMS delay spread for selected environments from reference 61. Okay, let us see reference 61. Okay, reference 61 is a book written by Theodore S. Rappaport. The title of the book is Wireless Communications, Principles and Practice, 2nd edition. The publisher is Prentice Hall, published in year 2002. Okay. Rappaport is a professor in New York University. His recent research includes 5G channel model measurement. Okay. When I was a student and took the course Wireless Communications, okay, my teacher used this book as the textbook. Okay, let us go back to page 109. Okay. So when the environment is urban in New York, okay, you can see that he measured in New York. Okay, so the frequency is equal to 910 megahertz. The RMS delay spread sigma tau is equal to 1300 nanoseconds. Okay, when the environment is urban in San Francisco and the frequency is equal to 892 megahertz, the RMS delay spread is 20,000 nanoseconds. When the environment is typical suburban and the frequency is equal to 910 megahertz, the RMS delay spread is equal to 300 nanoseconds. When the environment is extreme suburban and the frequency is equal to 910 megahertz, the RMS delay spread is 2000 nanoseconds. So you can compare the third row and fourth row. Okay, when the environment is more open, okay, that is with a smaller number of scatterers or objects in the environment, and under the same frequency, the RMS delay spread will be larger. Okay, this is because the length of the paths are longer, so the RMS delay spreads are larger. Okay, then in the environment of indoor, okay, in office buildings, when the frequency is equal to 1500 megahertz, the RMS delay spread is 25 nanoseconds. Excuse me. So when the environment is indoor in office buildings, the frequency is equal to 8 and 50/100 megahertz. The RMS delay spread is 270 nanoseconds. Okay, when the environment is indoor again in office buildings and the frequency is equal to 1900 megahertz, the RMS delay spread is equal to 90 nanoseconds. Okay, you can see that it is 1500 megahertz, and it is 1900 megahertz, and it is 25 nanosecond, and it is 90 nanosecond. So can we say that when in the same environment, when frequency increases, the RMS delay spread also increases? Okay, we cannot say this, because when frequency decreases to 850 megahertz, the RMS delay spread increases to 270 nanoseconds. Okay. So next, okay, let us go to section 4.4.1.2, coherence bandwidth BC. Okay, the coherence bandwidth BC is a measure of the range of frequencies over which a communications channel passes all spectral components of a signal with equal gain and delay. It is related in a simple way to the delay spread, as we will show shortly. To do so, we begin by defining the transfer function of a channel, capital C of TF, as follows. Okay, we can see that capital C of TF is defined as the integral from negative infinity to infinity, small c of t tau times exponential negative j2 pi f tau d tau. Okay, the equation number is in the wrong place. Okay, let me put it in the correct place. Okay. Okay, do you remember what is small c of t tau? Okay, let us review it. Okay, small c of t tau. Okay, small c of t tau is the impulse response function of the channel. Okay, let us go back to the slide. Okay, so we can see that the transfer function of a channel is equal to, I should say is defined as the Fourier transform of the impulse response function of the channel. And please note that the Fourier transform is taken on the variable tau, not variable t. Okay. Next, consider the autocorrelation of capital C of TF, which we denote by capital phi C of T1, T2, and F1, F2, and define as follows. Okay, capital phi C of T1, T2, F1, F2 is defined as 1 over 2 times the expectation of capital C complex conjugate of T1, F1 times capital C of T2, F2. Okay, please note that there is a factor 1 over 2 before the expectation. And there is a complex conjugate which is taken on the first, okay, capital C, that is the first transfer function. Okay, if we assume the channel is white sense stationary, then the autocorrelation will only depend on the difference in time, delta t. Okay, this is the definition of a white sense stationary channel. Okay, in that case, phi c of t1, t2, f1, f2 becomes phi c of delta t of f1, f2. Okay, so you can see the autocorrelation only depends on the difference in time delta t, but not depends on time instance t1 and t2. So this is equal to 1 over 2 times the expectation of C complex conjugate tf1 times C of t plus delta t f2. Okay, the equation number is not in the correct place. Let me fix this problem. Okay, good. Okay, furthermore, if we assume an uncorrelated channel, then the channel will be white sense stationary, uncorrelated scattering, and it can be shown. Okay, see end of chapter problems. Okay, let us see end of chapter problems. Okay, it is problem 4.2. Proof equation 4.27. Okay, let us go to equation 4.27. Okay, is this equation. Okay, that equation 4.26, okay, is the equation in the previous slide. Reduces to phi c of delta t f1, f2 becomes phi c of delta t delta f. Okay, it is because of the uncorrelated scattering. So the autocorrelation function only depends on the difference in frequency delta f, but not depends on the frequencies f1 and f2. So this is equal to the integral negative infinity to infinity small phi c of delta t tau times exponential negative j2 pi delta f tau d tau. Oh, the equation number is in the wrong place again. So let me correct it. Oh, sorry. So okay. So we can see that the autocorrelation function, okay, is equal of the transfer function is equal to the Fourier transform of phi c, function phi c. Okay, do you remember what is the function small phi c? Okay, let us review it. Okay, phi c of tau is called the multipath intensity profile, the delay power spectrum, or the power delay profile of the channel. Okay, which is equal to phi c of delta t tau 1 tau 2 is equal to 1 over 2 times the expectation of the square of the absolute value of small c of tau, where small c of tau is the impulse response function of the channel. Okay, let us go back to slide. Okay, maybe 110. Okay, oh, not this. Okay, this slide, where delta f is the difference between the two frequencies f1 and f2. Okay, if we consider a single instant of time, delta t is equal to 0. So capital phi c of delta t delta f becomes a function of delta f only, which we denote by capital phi c of delta f. Okay, that is phi c of delta t being equal to 0. Delta f is defined as phi c of delta f, and equation 4.27 reduces to. Okay, let us see equation 4.27. Okay, is this equation in the previous slide. Okay, so capital phi c of delta f is equal to the integral from negative infinity to infinity small phi c of tau times exponential minus j2 pi delta f tau d tau. Oh, the equation number is in the wrong place again. So let me correct it. Okay, good. Okay, so we can see that capital phi c of delta f is the Fourier transform of small phi c of tau. Okay, where capital phi c of delta f is called the spaced frequency correlation function. Okay, because here is the delta f. It is the differences of it is the difference between two different frequencies. So it is called the spaced frequency. Okay, and phi c is the autocorrelation function of the capital C, which is the transfer function of the channel. For the purpose of defining the coherence bandwidth, it is useful to define the normalized spaced frequency correlation function phi c prime of delta f, which is defined as follows. Phi c prime of delta f is defined as phi c of delta f over the maxima of phi c of delta f. Usually a function divided by its maxima, it is called the normalized version of the function. This is in the wrong place again. Good. Excuse me. So it follows that phi c prime has a maximum value equal to 1. Because phi c is divided by maximum of phi c. Equation 4.28. Let us see equation 4.28. Is this equation. Shows that the multipath power delay profile and the spaced frequency correlation function, the two key functions related to tau, are a Fourier transform pair as illustrated in figure 4. Okay, it is 25 minutes. Let us take a break.